Section 4.6, approximate integration using the midpoint and trapezoidal rules. Now remember, these are approximations. Fundamental theorem of calculus is a very powerful rule which allows us to evaluate the definite integral from a to b f of x dx. However, there do arise some occasions when it is not easy or even possible to find an antiderivative for the integrand. You'll get more of this on later. Or we may not be given a formula for a continuous function. So when we have this, we can use approximations by using geometric shapes that we know. We may be given an unknown function with values at certain points of closed interval a to b, which have been determined by experimental measurement. An example of this could be illustrated when measuring total distance traveled by a runner. Consider the runner's speed at certain time intervals. Do you know for a fact the runner is a long distance runner who is not stopping over the time interval? Could it be a sprinter who is walking between sprints? Do you see why the fundamental theorem of calculus doesn't address all integration problems? Now let's remember, a Riemann sum is one where the areas of the rectangles are used to approximate the definite integral. This technique is especially useful when the function is either not integrable or when it is not continuous over the interval. The rectangles can have the same width in each subinterval with y values evaluated at each of the left or right-hand endpoints, or they can have different widths. And I have to say that for AP exams, you're going to find this. Even with the trapezoidal rule, you're going to find that the widths are usually different. So you have to pay attention to that. Now, a closer approximation than either the left or right endpoint approximations for the integral appears to be a midpoint approximation. This method uses the midpoint of each subinterval and the y values determined by each midpoint. If you are working with data which does not give a y value for the midpoint value, you must not assume that that y value is the average of the left and right endpoint y values. This would be a critical error, and we've talked about that in class. So this rule looks really terrible, but it's not. It's just that we're going to approximate the integral by midpoints. So this is the standard delta x. Each rectangle is the same width. And then that line above the x means the midpoint or the average. So evaluate at the midpoint of the first subinterval, the second subinterval, and so forth. And your delta x, of course, is b minus a over n. And your xi bar is 1/2 the next x plus the current x. Okay. In other words, find the midpoint of each subinterval, then find the corresponding y coordinate, then add up the areas. Okay, this is not hard. We've done this before. So here's my integral. We're going to make 5 subintervals. So on the interval from 1 to 2, b minus a over n gives the width of each subinterval to be 1/5 or 2/10. My subintervals would therefore be 1 to 1.2, 1.2 to 1.4, 1.4 to 1.6, 1.6 to 1.8, and 1.8 to 2. Now, the midpoints of each of these would be 1.1, 1.3, 1.5, 1.7, 1.9. I'm going to evaluate these x coordinates in our function. So here we have that. And I have my integral is going to be very important. We're going to use that approximation symbol. My delta x, which is 0.2 or 1/5, and the y coordinates evaluated at each of those x's. And I get this. Now, this actually is an integral we can actually evaluate using the fundamental theorem of calculus, and you're going to learn that in the next video. It turns out that the integral of 1 over x is natural log of x. You'll notice here's what 1 over x looks like. Here's what natural log of x looks like. Notice that natural log of x is very rapidly increasing at the beginning and increasing at a slower rate as we go this way. Look at its derivative, very high y values representing a steep slope and getting closer to 0 representing a slowing down of the increase. Okay, so the integral from 1 to 2 of 1 over x is going to be natural log of x from 1 to 2. You have to use your calculator, and look, we get that value, which is pretty darn close to our approximation. As a general comment, when you see 1 over x dx, you cannot convert that to an x to the negative 1, add 1 to the exponent, divide by the new exponent. No, we can't do that. So we're going to learn this in the next section. These are nice little diagrams of the curves that you have seen. Here is our left endpoint approximation of this curve. Here is our right endpoint approximation. Here is our midpoint approximation. You can see that the midpoint generally gives a better approximation than either the left or the right. But what would give a better approximation than midpoint? The trapezoid. Look how little area is left out when we use a trapezoid approximation. And by the way, a trapezoid approximation is your right and left-hand sum averaged. The midpoint is not the average of the right and left-hand sums, amazingly. It is the trapezoid approximation that is. When would we want to use something like the trapezoid rule? Well, gosh, that seems just to give us overall a much better approximation. When would we want to use something like a trapezoidal approximation? Let us imagine a ship at sea. It's easier to measure how fast you're going than how far you've gone. Suppose you are a navigator aboard a supertanker. The speed of the ship is measured each 15 minutes and recorded in a table shown. Estimate the distance the ship has gone from 7:30 p.m. to 9:15 p.m. We're going to be using a graph. All right, so starting at 7:15, here are these speeds. And I'm going to show you this diagram. Pause the video and draw in this trapezoidal diagram. So what we have done here is we have plotted each one of this is our velocity, this is our time, and this is our time in minutes or quarter of an hour, right? And this is velocity in miles per hour. And we've plotted those points and sketched our little trapezoids. Now you know from geometry that the area of this trapezoid here would be 1/2 this length, which is 1/4 of an hour, times base 1 plus base 2. This would be 1/2 times this length, 1/4 of an hour, base 1 plus base 2. 1/2 this length, base 1 plus base 2. Do you notice that all of these are used twice and this is used once, and by the time I get down here, this length will be used once? That's what this represents. The two arrows show the values that are used only once, and all of these are used twice. So here is our trapezoid formula. One trapezoid, our first trapezoid, 1/2, 1/4 of an hour, base 1 plus base 2 gives us that area. And again, it's taken every 15 minutes, but we want our hours units to cancel out. This is hours right here, and this is miles per hour. So the hours units will cancel out, leaving miles. Okay. And we go through the process for the whole set of data, and we get that in that time from 7:30 to 9:15, we traveled 33 miles. Pretty neat. Seems like a lot of work. Shorter and easier method. Well, you could take the left and right endpoint, Riemann sums, and average them. Why? The left endpoint, if I made a rectangle, I would use this one, this. If I did a right one, I would use this. You'll notice these are getting used twice. This is getting used once. That's how it's done. So areas using the trapezoids in the last example could have been found using a simplified method, and that is 1/2 the height of each trapezoid, which was 1/4 of an hour, and then the first and last measurement used once and all of the others used twice. That'd be easier than individually finding each area like we did right here. Okay. So this leads us to the trapezoidal rule. The trapezoidal rule says, here's our formula, 1/2, our delta x, b minus a over n, the first x and last x, the y coordinate evaluated at those, and then all of the other x's, the y gets used twice. You could also write it like this. Your exterior bases are counted once, your interior bases are counted twice. So let's go back to the very first example that we did. The integral from 1 to 2 of 1 over x dx with 5 subintervals. We found our delta x to be 0.2. And our formula calls for 1/2 delta x, so 0.2 over 2. Notice I'm going to approximate using a trapezoidal approximation. The first and last x's evaluated and used once. The interior x's, okay, 1.2, 1.4, 1.6, and 1.8 evaluated and used twice. And here's what we get. Now let's recall the midpoint approximation was 0.691908, and the actual value of this integral is 0.693147. Let's remember, when we calculate an integral, when we do it using a rectangular or trapezoidal approximation, we have the approximation plus whatever error we have, which would give us the actual value of the integral. So our error using the trapezoidal rule was, notice that we got this, but the actual is this. Okay, so the error is we're off by 0.002488. And our error using the midpoint rule, it was our midpoint rule, okay? So our actual integral is 0.001239 larger than this. Our actual integral for trapezoid rule is 0.002488 less than this. So we'd call this our error. Now, important thing to know is in mathematics, when we talk about error, we don't usually say plus or minus, we just say the error is. So if we increase the number of subintervals, our approximations are going to be closer to the definite integral, and our corresponding errors will decrease. Observations that are true in most cases. More accurate approximations result for all methods as the number of subintervals increase. Trapezoidal and midpoint rules are much more accurate than endpoint approximations. The size of the error in the midpoint rule is about half the size of the error in the trapezoidal rule. Look at that. That's kind of a neat observation, isn't it? Interesting properties. This is a key. If a function is concave up, a trapezoid approximation will overestimate and a midpoint will underestimate. If a function is concave down, a trapezoidal rule will overestimate and a midpoint rectangular approximation will overestimate. Now, in our BC topics, those of you in BC, we will more fully investigate error later. It's a pretty important topic. Prior to today's lesson, this is what you knew. Left sum and a right sum. You might want to draw those in. We had done a little experimentation with our midpoint sum. And today we concluded with trapezoidal sum. Your TPs for the trapezoidal rule are number 5 and number 39. Use the trapezoidal rule only. See you next time.